NEC Section 450.13c addresses the requirement for a disconnect switch or circuit breaker for transformers. This code section mandates that a main disconnect switch or circuit breaker shall be provided for each transformer. The disconnect switch or circuit breaker shall be readily accessible and shall be located as close as practicable to the transformer. The primary reason for this requirement is safety. The main disconnect switch or circuit breaker provides a means of energizing the transformer for safety purposes such as maintenance or repair. In situations where the disconnect switch is located far from the transformer, accessing and energizing the transformer in an emergency becomes difficult. The code specifies that the disconnect should be readily accessible and as close as practicable to the transformer. This ensures that in emergency situations or during maintenance, personnel can quickly and safely de-energize the transformer. The term readily accessible means that the disconnect should be easily reached without having to climb over obstacles or remove barriers. As close as practicable means that the disconnect should be located as near to the transformer as is reasonably possible, taking into account the physical layout of the installation and any other relevant factors. In a scenario where a transformer is fed from a 400 amp service with a 400 amp main breaker, and the transformer is located 80 feet away from the service, the installation would not be code compliant without a disconnect located near the transformer. The considerable distance between the main service disconnect and the transformer violates the requirement for the disconnect to be located as close as practicable to the transformer. To achieve code compliance, a disconnect switch or circuit breaker must be installed close to the transformer. This disconnect should be rated for the full load current of the transformer. The location of the disconnect should be readily accessible, ensuring that it can be easily reached in case of an emergency or for maintenance purposes. Firstly, calculate the full load current of the transformer. The transformer's kilovolt ampere rating, which is 150 kilovolt amperes, and the system voltage are required for this calculation. Assuming a three-phase 480 volt system, the formula for calculating the full load current is kilovolt amperes times 1000 divided by the product of the voltage, which is 480 volts, times the square root of 3. This yields approximately 180.4 amps. Secondly, select a disconnect switch or circuit breaker that is rated for at least 180.4 amps. It is generally recommended to choose a slightly higher rating to account for any potential future increases in load. A 200 amp disconnect switch or circuit breaker would be a suitable choice in this case. Thirdly, install the disconnect switch or circuit breaker as close as practicable to the transformer. Follow all applicable electrical codes and standards for the installation. Ensure that the disconnect is readily accessible and properly labeled. It is essential to verify the specific requirements of the local electrical code, as interpretations and amendments may vary. Consulting with a qualified electrical inspector or engineer is highly recommended to ensure that the installation meets all applicable requirements. The NEC provides specific guidelines for transformer protection, including overcurrent protection requirements outlined in Section 450.3. The overcurrent protection devices, such as fuses or circuit breakers, are designed to protect the transformer from damage due to overloads or short circuits. These devices must be sized appropriately based on the transformer's rated current and impedance. For transformers rated over 600 volts, NEC Section 450.3 provides specific requirements for overcurrent protection. The primary overcurrent protection device must be rated or set at no more than 125% of the transformer's rated primary current. If the primary current is 9 amps or more, a circuit breaker may be used set at not more than 125% of the rated primary current. If the primary current is less than 9 amps, the overcurrent protection device must be rated or set at not more than 167% of the rated primary current. If the primary current is less than 2 amps, the overcurrent protection device must be rated or set at not more than 300% of the rated primary current. The secondary overcurrent protection device must be rated or set at no more than 125% of the transformer's rated secondary current. NEC Section 450.4 addresses the requirements for transformer grounding. Transformers must be properly grounded to ensure safety and prevent electrical shock hazards. The grounding requirements vary depending on the transformer's voltage and configuration. For transformers with a secondary voltage of 150 volts or less to ground, the neutral point of the secondary winding must be grounded. This grounding connection must be made in accordance with NEC Section 250.30. For transformers with a secondary voltage of more than 150 volts to ground, the grounding requirements are more complex and depend on the specific application. In general, a grounding electrode conductor must be connected from the transformer's secondary neutral point to a grounding electrode system. The grounding electrode system must comply with NEC Section 250.50 and may include a metal underground water pipe, a ground ring, or other approved electrodes. NEC Section 450.11 covers the requirements for transformer clearances. Transformers must be installed with sufficient clearances to allow for proper ventilation and maintenance. The required clearances depend on the transformer's size, voltage, and location. In general, transformers should be installed with at least 3 feet of clear space in front of the enclosure to allow for access and maintenance. Clearances around the sides and rear of the transformer may be reduced depending on the specific installation. Transformers installed indoors must also comply with the requirements of NEC Section 450.21, which addresses ventilation and fire protection. Transformers installed outdoors must comply with the requirements of NEC Section 450.22, which addresses weather protection and security. NEC Section 450.14 discusses the requirements for transformer wiring. The wiring methods used to connect transformers must comply with all applicable requirements of the NEC. Conductors must be sized appropriately for the transformer's rated current and must be protected from overcurrent. The wiring must be installed in a neat and workmanlike manner, and all connections must be properly made and tightened. For transformers rated over 600 volts, the wiring must comply with the requirements of NEC Article 310, which covers conductors for general wiring. The conductors must be insulated for the voltage involved and must be installed in a raceway or other approved enclosure. When extending busbars with 500 MCM conductors to a 150 kV ampere transformer, several factors must be considered to ensure code compliance. Firstly, the ampacity of the 500 MCM conductors must be sufficient to carry the full load current of the transformer. As calculated previously, the full load current of the transformer is approximately 180.4 amps. According to NEC Table 310.16, the ampacity of 500 MCM copper conductors with a 75 degrees Celsius insulation rating is 380 amps. Therefore, the 500 MCM conductors are adequately sized for the transformer's full load current. Secondly, the conductors must be properly protected from overcurrent. Overcurrent protection can be provided by a circuit breaker or fuses located at the source of the conductors. The overcurrent protection device must be sized appropriately based on the ampacity of the conductors and the transformer's rated current. In this case, a 200 amp circuit breaker or fuses would provide adequate overcurrent protection for the 500 MCM conductors and the transformer. Thirdly, the conductors must be installed in a raceway or other approved enclosure. This will protect the conductors from physical damage and prevent them from coming into contact with other objects. Suitable raceway types include electrical metallic tubing, intermediate metal conduit, and rigid metal conduit. Fourthly, the connections between the busbars, conductors, and transformer terminals must be properly made and tightened. Loose or corroded connections can cause overheating and arcing, which can lead to equipment failure and fire hazards. All connections should be made using approved connectors and should be torqued to the manufacturer's specifications. Finally, it is essential to verify the specific requirements of the local electrical code, as interpretations and amendments may vary. Consulting with a qualified electrical inspector or engineer is highly recommended to ensure that the installation meets all applicable requirements. In summary, while the 500 MCN conductors are adequately sized for the transformer's full load current, the absence of a disconnect switch or circuit breaker located near the transformer violates NEC section 450.13c. To achieve code compliance, a disconnect must be installed close to the transformer, and all wiring and connections must be made in accordance with the NEC and local electrical codes.